Dear students, today we are discussing on the subject Logic System Design. In this session, we are focusing on arithmetic algorithms in Module 5. As the name indicates, these are different algorithms for performing arithmetic operations of binary numbers. Now we can check which are the main algorithms specified in our syllabus. First one is algorithm for addition and subtraction of binary numbers in sign magnitude representation. Next one is addition and subtraction of 2's complement representations. And the third one is algorithm for addition and subtraction of floating point numbers. And the last one is algorithm for addition and subtraction of BCD numbers. Before going deep into the algorithm, first we have to understand how a signed binary number can be represented. A signed binary number can be represented using three different methods. First one is sign magnitude representation, second one is 1's complement representation, and the third one is 2's complement representation. First, we shall check how a signed binary number can be represented using sign magnitude representation. Here an example is given. Here plus 43 is represented in sign magnitude form. Here we can see that the most significant bit is allocated for representing the sign of the number. If the sign bit is 0, it indicates the number is a positive number. And if the sign bit is 1, it indicates the number is a negative number. Here we have represented plus 43. So the sign bit here is 0. And the rest of the bits represents the magnitude or the value of the number. We all are familiar with how a magnitude of a binary number can be calculated. It is based on the place value of the digits. Here, since it is a binary number, the base is 2. So the binary equivalent of decimal 43 is calculated in this way. So 101011 represents the decimal 43. That is, this can be represented like this: 1 into 2 raised to 0 plus 1 into 2 raised to 1 plus 0 into 2 raised to 2 plus 1 into 2 raised to 3 plus 0 into 2 raised to 4 plus 1 into 2 raised to 5. This will give the magnitude 43. So a binary number can be represented using the place value of the digits. Here the base is 2, so here we are taking the power of 2. We all are familiar. This binary power can be represented, can be easily represented using 8421 values. 8421, these values represents 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, etc. If we have to represent a bigger number, we need to extend these values. Now we can check how a number can be represented in 2's complement and 1's complement representations. In the case of 1's complement representation, we have already written plus 43. We can again take the same example. For 1's complement representation, we just need to flip the digits 1 to 0, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 0 to 1. So just by flipping the digits, we will get the 1's complement of the number. So this is the 1's complement representation of minus 43. In order to represent the number in 2's complement, first we have to take the 1's complement of the number and just add 1 to the 1's complement representation. So this is the ones complement, and we have to add plus 1 to this value. We will get this value as the result. This represents minus 43. This is the 2's complement representation of minus 43. We can consider one more example. Here in this example, we have considered the number plus 9 and minus 9 in 7-bit binary number representation. So plus 9 can be represented as, we all know, for representing 9 we need only 4 bits, but here we are using a 7-bit representation, so we are extending 2 bits by using 2 zeros, and 1 bit is dedicated for representing the sign of the number, since it is sign magnitude representation. 0 indicates the number is positive. In sign magnitude form, we can represent minus 9 also. For minus 9, we have to change the sign bit from 0 to 1. In ones complement representation, we need to flip all the digits, that is 0 to 1 and 1 to 0, and we will get the ones complement representation of this plus 9. So this is the ones complement representation of plus 9. For representing it in 2's complement, we just need to add plus 1 to this ones complement representation. So this is the 2's complement representation of minus 9. We just need to add plus 1 to this value. For sign magnitude number, we are storing, or we are saving the number in a register called accumulator register, and the sign bit will be stored in the AS bit position. If a sign magnitude number Z can be represented as AS comma A, where AS is the sign of the sign magnitude number and A is the magnitude of that number. The leftmost position AS is the sign bit. If the sign bit is 0, that is, if AS value of AS is 0, then the number will be a positive number, and if the value in AS is 1, the number will be a negative number. So A subscript S represents the sign bit of the number, and the value will be, complete value will be in the accumulated register. The sign bit will be indicated as A subscript S. Now we shall move on to the algorithm part. Before going to the algorithm, we can check what all are the possible operations while performing addition and subtraction of binary numbers in signed magnitude representation. While performing addition and subtraction, these are the possible operations we come across with. So the first 4 operations listed in this table are for addition, and the rest of the 4 operations represents the subtraction operation. In the first 4 operation, each operation can be distinguished based on the sign of the numbers, that is, whether the first number is positive or the second number is positive or negative, and also whether which number is greater, whether A is greater or B is greater, and also based on the operation, whether it is an addition operation or the subtraction operation. So these are the possible operations come across with while performing addition and subtraction of signed magnitude binary numbers. So in the addition section, we can see that if both the numbers are positive or both the numbers are negative, that is the sign of A and B are same. If the sign of A and B are same, that is the first one and the last one. If the sign of A and B are positive, or if the sign of A and B are negative, both are positive or both are negative, in that case we are following the same mathematical principles. That is, we are adding the magnitude values and giving the common sign. In the case of if both the numbers are positive, we are adding the magnitude values magnitudes of A and B, and we are giving the common sign. If both the numbers are of different sign, that is first number is positive and the second number is negative, in that case we have to find the difference of the numbers. So in that case we need to check an additional checking, that is whether A is greater or B is greater. If A is greater, we are subtracting B from A, and since A is greater, according to the mathematical principles, we are giving the sign of the greater number, that is positive. So the resultant will be positive. If B is greater, we are subtracting A from B and we are giving the sign of the bigger number. Here the bigger number is B, so the sign of B is negative, so the result will be a negative number. There is a third condition also. If A and B are same, A and B are of equal magnitude, A equal to B, in that case the answer will be 0. A minus B will be 0. The resultant will be 0. We are just giving the sign. There is no significance of sign in that case. Okay, in the third third case also, if A is negative and B is positive, in that case also we have to perform subtraction operation, since both the numbers are of different sign. According to mathematical principle, we have to perform the difference operation, and then based on the magnitude, if A is greater, we have to give the sign of A. If B is greater, we have to give the sign of B. Okay. In the fourth case, that is the sign of both the numbers are same, in that case we just need to add the magnitude and give the common sign. Here both the numbers are negative, so here we are giving the common negative sign to the resultant value. Okay. In the last possible operations, that is subtraction operations, here also the same condition checking and same policies are followed. Here we can see that in the first case both the numbers are of same sign, that is both are positive. In that case, according to mathematical rule, A minus plus B is actually A minus B. We have to perform the difference operation. So based on the magnitude value, that is whether A is greater or B is greater, we have to give sign to the resultant. In the second case also, plus A minus B, in that case we know that minus B becomes positive, so we can add the magnitudes of A and B, and both the sign will be same, plus sign will be given to the resultant. In the third case, both the sign are minus A minus plus B. In that case both the signs are negative. In that case also we can add the magnitude values and give the minus sign. The last case is minus A minus B. In that case minus A, it becomes minus A plus B. In that case we have to perform difference operation, and we have to give the resultant sign according to the magnitude. Okay, so these are the possible operations we come across while performing addition and subtraction of binary numbers in sign magnitude representation. So in the algorithm we are addressing these operations. Okay, we are addressing these 8 operations. For addition operation, we are come across with these 4 conditions, and for subtraction we are come across with these 4 conditions. Okay, now we shall look on the detailed flowchart of the algorithm, that is addition and subtraction of sign magnitude numbers. So based on the operation, if we are performing an addition operation, flowchart or algorithm will start from here. If we are performing subtraction operation, we will start from here. Okay, first we shall check with addition operation. In the case of addition operation, augment in A, addend in B. So the first number will be in A register and the second number will be in B register. First we need to check whether both the numbers are of same sign or different sign. This is performed based on the logic of XOR operation. Here we are performing XOR operation of AS and BS. AS means the sign bit of first number will be saved in A register and the sign bit will be indicated using A subscript S, and second number will be saved in B register and the sign bit of second number is indicated as BS. So we are performing an XOR operation of AS and BS. According to the XOR operation, we know that if both the inputs are same, the output will be 0. If both the inputs are different, the output will be 1. Here, if both the inputs are same means both the numbers are of same sign. Okay, so if both the numbers are same sign, in the case of addition, we have earlier we have seen in this table that if both the numbers are of same sign, plus A plus B or minus A minus B, in that case we just want to add the magnitude values and giving the common sign to the resultant. So that is performed here. If both the sign bits are XORed here, if both the sign bits are same, the XOR operation output will be 0 and it is AS equal to BS. So we move on to this step, that is we are just adding the magnitudes. Magnitude portion will be in A and B. These magnitudes will be added and the resultant will be moved on to the A register itself. Okay, A register is accumulated register. The result value will be moved on to the accumulated register. What is this E indicates? E is used to store the end carry generated during this addition operation. There are possibility of end carry generation. That end carry from the MSB point can be stored in a single bit register or flip-flop called as which we named as E. Also we have an additional flip-flop for indicating overflow. Add overflow flip-flop, it is indicated here. If there is overflow, that is overflow means if both the numbers both the numbers are 8 bits, if there is an end carry generated at the MSB point and if the resultant is changed to a 9-bit value, then we can say that an overflow has occurred. That will be indicated using this flip-flop. It is also a single bit flip-flop. So as we have already mentioned, if both the signs are same, we are just adding the magnitudes and giving the same sign, and the end carry can be saved inside this E register, single bit E register. Also if there is an overflow, it can be indicated using this add overflow flip-flop. Okay, the next condition is if both the sign are of different. Both the sign different means both the numbers are of different sign. In that case, we have to perform difference operation or subtraction operation. So we are moving on to if AS XOR BS is equal to 1. That means both the numbers are of different AS and BS, either it can be 0 1 or 1 0. In that case, one number will be positive or the other number will be negative. In that case, we are moving on to subtraction operation, which we have already seen in this table. If both the numbers are of different sign, that is plus A minus B or minus A plus B. In that case, we have to perform the difference operation and we have to give the resultant the sign based on the magnitudes. Where if A is greater, we have to give the sign of the greater number. If B is greater, we have to give the resultant the sign of B. Okay. If both the numbers are same, the result will be 0. So if we are moving on to this side, and if AS is not equal to BS, we are performing A plus B complement plus 1. While doing subtraction operation, we are taking the complement of the second number, that is here the second number is B. We are taking the complement of B plus 1 means here we are performing 2's complement subtraction. In order to perform 2's complement subtraction, first we have to find the complement. First we have to find the 1's complement of B, then plus 1. 1's complement plus 1 means 2's complement of B. So we have find out the 2's complement of B and that value will be added to the A. Okay. Now we got the result in accumulated register, and here also since we are performing addition, there is possibility of n carry. N carry will be stored in E register. Here also there is possibility of overflow. Initially overflow flip-flop is initialized with a 0, and here we are again checking whether n carry is generated or not. If the n carry is 1, that is if there is a carry in the 2's complement subtraction, we need to note that if there is an n carry, there is no problem. We can proceed towards, we can take that result and we can discard that n carry generated, and we can stop the operation and the result will be in A. But if there is no n carry, that is no carry is generated, in that case the resultant in A is not the correct result. In order to get the correct result, we have to find again 2's complement of A, then only we will get the correct result. The result generated will be in 2's complement form, so we have to find once again complement of the that result value, then only we shall reach the final result. So if the n carry is 0, in that case we have to complement A. We have result in A, so we have to again complement A, that is A complement is here in A, then that A complement plus 1 is added here, so we have find out the 2's complement of A. So we have again complemented the result and we have changed the sign also. Then we can end the result. Now we got the, after finding the 2's complement of the result, we get the final result. We got the final result. Now we check with the subtraction operation. In the case of subtraction operation, the first number is in capital A register and the second number is in B, that is minuend in A and subtrahend in B. Here also the logic is same. Here also we are checking whether here also we have to check whether both the numbers are of same sign or both the numbers are of different sign. If both the numbers are of different sign and subtraction operation, in that case we are adding the magnitude. If both the numbers are of same sign, we are performing a difference operation. So same logic is followed here also. Here we are performing the XOR operation of the sign bits. If both the sign bits are of same value, that is A XOR B gives output as 0, that is sign bits are same, in that case we have to, in the case of subtraction, we have to perform difference in that case. If both the sign bits are different, in that case we have to perform addition, that is we are adding the magnitude, so we have to move on to this side. So this is the overall logic of the sign magnitude addition and subtraction. The only thing we need to check is that whether both the numbers are, we need to check the sign of both the numbers. If both the numbers are of same sign, we need to follow the same principles we used in mathematics. If both the numbers are different sign, then the same principles and policies we used in mathematics is followed here in this algorithm also. So this is the overall idea of this sign magnitude addition and subtraction. I hope you understand the concept. Thank you. If for more queries, contact me at this email address. Thank you.